Welcome back, everybody. We finished up 1.6 and now we're on to 1.7, which I would rather call properties of functions and piecewise functions. But either way, we have the properties. So first things first, we got a big definition to deal with. So let f be some function defined on an interval a to b. Doesn't matter what that interval is, could be 5, 7, who cares? The function is said to be increasing on a comma b if f of x sub 1 is less than f of x sub 2 for all x sub 1, x sub 2 in the interval. Sorry, I'm going to restart the app because it's just, I think I just need to go through and wipe memory, but either way. So a function is said to be increasing on a comma b if f of x sub 1 is less than f of x sub 2 for all x sub 1 less than x sub 2 in the interval. So let's try and visualize that. So that's it in mathematics, but what does it mean visually? Well, if we remember what f of x sub 1 is and what f of x sub 2 is, those are the y values, they're the function values associated with x sub 1 and x sub 2. So let's say this is x sub 1 here, and this is x sub 2, right? Then x sub 1 is less than x sub 2, two generic points that I can pick anywhere. And then the corresponding y values will be f of x sub 1 and f of x sub 2. And we see that the points, the f of x sub 1 value is smaller. It's closer to the to 0 than f of x sub 2. So this is going up. This is increasing by definition. The intuition is that if you're a little guy on this thing, or girl, or her person, you're walking uphill. When you go from left to right. That's what it would mean to be increasing, is you're walking up a hill as you go from left to right, because we read our graphs from left to right. A function is said to be decreasing if on a comma b, f of x sub 1 is greater than f of x sub 2 for all x sub 1 less than x sub 2 in the interval. So the only thing that's changed in this definition is the word decreasing and then the sign, the direction of the inequality. In the context here, that would mean that the y value of x sub 1 is larger. So if you're further left, you're higher up. Once again, we've got x sub 1 here, x sub 2 here, and you'll see that f of x sub 1 is higher up. It's above the x-axis, so it's a positive number, whereas f of x sub 2 is a number below the x-axis. It's negative. And so by a similar intuition argument, if you're a little dude walking along, it's decreasing if you're walking downhill. All right. A function is said to be constant on a comma b if f of x sub 1 equals f of x sub 2, meaning that the y values are always the same. The y values are always the same between a and b, no matter which values you pick. And so here's x sub 1, here's x sub 2, and then this point is f of x sub 1, which equals f of x sub 2. They're the same point, the same y value. And so looking at it from the perspective of a little ant guy or girl, they're walking on flat land. So those are the three main types of ways to describe a function's behavior as it moves from left to right: increasing, decreasing, or constant. Now, I believe this problem is still in the notes, and I want to mention it because it's an important thing, because it's a big difference. So, problematic example 1.7.1. The graph of function g is given below with the points a through e. Determine if g is increasing, decreasing, or constant from those perspectives. So from a to b, increasing or decreasing? Increasing. Yes. So I'm just going to write INC for increasing and DEC for decreasing, so we don't have to keep writing those words. From B to C, constant. From C to D, decreasing. And from D to E, it's increasing. So why is this example problematic? Why is this example problematic? It has to do with one problem that is like one of the problems is mathematical, like is mathematical a problem with mathematics, and the other one is a problem with the terminology. So the thing is, we typically want intervals of increasing slash decreasing slash constant. As such, it doesn't make sense to talk about it in terms of points. Additionally, one of the big problems with mathematics, in my opinion, especially pre-calculus, like 100 level math courses, because it's still when you're learning this stuff. Without context, what is this? Is that a point or is that an interval? I didn't tell you. It could be an interval. It could be a point. And so by using the point situation here, you're going to get yourself confused thinking that you need to write you can write your intervals in terms of points, but you can't. It's based on the x values of the points. It's based on intervals of x. So this is a improved version of that question. Graph of G is given below for points A through E. Determine the intervals on which G is increasing, decreasing, and constant. So when you're looking for increasing, decreasing, and constant, I'm going to color code them. Let's do increasing. What do you guys think? Is increasing red or blue? Interesting. I had red originally, but we'll do blue. Decreasing will then therefore be red, and constant, let's go with purple. Those are all different colors. Like you can see the contrast. So the way I typically do this when I'm starting out, I don't do this anymore because I've been doing this for so long. But when you're starting out, it might be helpful to highlight the pieces that are increasing, decreasing, and constant. So we already knew that it's increasing from A to B. So we'll draw that piece right there. We knew that it was increasing from D to E right there. We knew it was decreasing from C to D. And we knew it was constant from B to C. These are, we want X intervals. So zooming in on the graph for a second, we want X intervals. There's two intervals that it's increasing on. It's hard to see the dashed lines. I'll make sure that on the exam it's very, very clear. But what's the first interval it's increasing on? From A to B, but what are the X values? -5 to -3. So that's the first interval. So -5 to -3. Now, some textbooks will say that you should use brackets, and some textbooks are wrong. It's not correct. Brackets it drives me nuts when there's a textbook that says that. It should be parentheses. It should be. because there's no sense in talking about the endpoints because at the endpoints of these things, it could go up or down. So you're like, it's dumb. It's dumb and I hate it and it's stupid. And we will not be doing that. We will be using parentheses like good mathematicians. And the second one, so we're talking about these in terms of not their coordinate points, but in terms of their x coordinates from their x values. So the next one should be, the next interval should be from what? Looking at the graph, I'll zoom in a little bit better. From 4 to 6. Now here's the big question though. Do I do a union symbol or do I do a comma? I wrote a comma, and that is technically correct. The answer is it varies. This is one where ambiguity is okay. Technically speaking, the commas have won out. There was a huge battle, gun battle specifically in a mathematics education like conference in Paris. Massive amounts of mathematicians dead. It was horrible. As a bad day to be a mathematician. Good day for the rest of the world, though, right? No more mathematicians. But the comma people won out. The comma mathematicians said that it should be commas, and the last man standing was a comma person, so they won out. The argument for why it should be a comma is that if you say it's a union, you're saying that it's increasing over that entire thing. So then it would have to be, so like the argument was, if I say this, then I'm saying that's increasing throughout that period. So f of 4 should be larger than f of -3. That would be the argument that they'd make. Whereas if it's a comma, it's saying it's increasing on those two things separately. One might be larger than the other, but it doesn't matter. On those two individual pieces, it doesn't. On an exam, if you use a union symbol, I'll give you full credit. It does not matter to me, but I believe Alex likes to use commas unless they've changed things. That's the general convention. Decreasing. Remember, it's x intervals, not points. 1 to 4. It's really hard to see. I promise my graphing grid on an exam will be a lot better than this. This was stolen like directly from Alex, actually. So copyright infringement, maybe. I'm not making you pay for it, so should be fine. And so from parentheses 1 to 4. And then constant from -3 to 1. Okay. Any questions on that? What's the name again? Go back there. Preston, do you have a question? Okay. All righty. Next one. I want you guys to find out parts A, B. I want you guys to fill in all of them. I'll slowly fill in details. I think we can do this problem now. Zoom in if you want to look at it better. First thing is the domain. You feel comfortable not color coding your increasing, decreasing, constant? Be my guest. But it's just as you're starting out. All right, I've got parts A, B, and C up here if you'd like to check your work. I'm wondering if anybody's, what's the value of part D? Has anybody gotten that one done yet? What's the value of D? 1. Yes. It's trying to be what I like to call a Canadian goose, which makes no sense unless I give you context. If you've ever encountered a Canadian goose, they're very territorial and they start to like run after you. You know what I'm talking about? And they try and bite you. But unless you know the trick, my wife didn't know this until she was until we were engaged. So she went 27 years without knowing it. When did we get married? Doesn't matter. Just kidding. But anyways, all you have to do is just buff out your chest to a Canadian goose, and it will run away. So you just need to stand bigger and taller than it and be more scary, and it'll run away. Thing is, that's trying to be a scary problem. What I have to find out what f of 4.3769895 is. That's a really hard number to find out. How am I going to do it? It's not. It's just trying to trick you. I'm going to color code it with pink. 4.37. What is it? 4.3 76895 is right about there. And so what is the h of that value? That's going to be the corresponding y value. And since it's on a constant plane, since it's on a constant portion of it, it's going to be that y value of 1. So since h is constant on 4 to 6, h of 4.3769895 is equal to 1 identically. It's trying to scare you, but it's not actually that scary. Yes, Laisha.
In the when I'm listing the intervals,
Mhm.
the increasing, you separate them with commas, but I was taught to separate them with
The U.
a semicolon. No,
Oh, with a
with a
semicolon?
just to differentiate, like from the comma that's in the parentheses to the one that's outside.
Fair enough. That's
Um,
okay.
so
No, it does not matter to me. As long as they're separated in some way, shape, or form, I'm okay with it. Alex will want them as commas. I'm fairly confident on that one, unless it's changed since last semester. All right. Any questions on any part of those? We didn't go over it, but I hope we kind of see how to find the increase and decreasing. Okay. Domain range was mostly just a review. And so we have the next thing. The next definition, 3-part definition. We have another aspect we can study about functions and their graphs. So let f be a function defined on some interval. The function is said to have a relative maximum, sometimes, or no, I'm just going to put, or local. Some textbooks will say local. So if you're looking up and you see someone say local minimum or local maximum, that may mean a relative maximum. Our textbook uses relative, but I think it's an older term, but local is still usable. So you have a relative maximum at x equals a if there exists an open interval. Could be really, really tiny, could be really, really large. It doesn't matter. But at least as long as there's one open interval around x equals a, such that, oh, I have to write this. I have to write this. I hate it. F of a is greater than or equal to f of x for all x in the interval. It should be. It should be. It should be f of x. F of a is strictly greater than f of x. It should be. And it's not because they're wrong. Miller and Gherkin are pretty good mathematicians, but they're wrong here. They're 100% wrong, and I'll tell you why. Because I have to, because it's driving me nuts every single time I teach this course. By that thing's definition, that's a relative maximum. That's a relative maximum. All these points are relative maximums by its definition. Because on all those points, f of x or f of a is greater than or equal to all f of x around the interval. Greater than or equal to. And that's dumb. That's dumb. That's stupid. That's not a max. A max should be a little hill. So I'm sorry. I just got to get. I'll get off my soapbox and my frustration. But that's the way the book describes it. I would argue that it should be f of a is greater than f of x. But digress. So that's f of a, which means that that's x equals a. So this is f of a. And you can see that you can find a little tiny interval. You can actually find any interval for this one, but as long as you can find at least one interval, this is an interval around A, such that while you're on this interval, all the f of x values are below it. All the a value, like all the other x values are below it. And so if you're thinking about it in terms of a little person, I mean, it could be a cat. You could draw a cat if you want. The person is at the top of the hill. That's how you know you're at a relative maximum. Graphically, like picturally, like as a picture, you'd be at the top of a hill, and then similarly, a function is said to have a relative or local minimum at x equals a if there exists an open interval around a such that f of a is less than or equal to f of x for all x inside the interval. The reason why they do it, by the way, is so that they can say for all x, when they could just bypass that by saying f of a is greater than f of x for all x not equal to a in the interval, but they don't. And so once again, that's a. This is f of a. And so if you draw a little interval around a, you can see that every other point has a larger y value. Every other point in that little space, the y values are larger. And so if you're a little doggy, the dog is at the bottom of a valley. It should be a dog. Make sure it's a dog. It actually doesn't matter, but I'm getting sidetracked. So those are the two things, and there's only I misspoke. There's not three parts. There's only two parts. There's relative maximum and relative minimum. So here's a little problematic thing about the jargon issue. So f of a is the relative max / min value. And it occurs at x equals a. The point a comma f of a is the relative max / min. This is kind of like a semantics. I always get semantics and syntax messed up, but I believe it's a semantics argument here. It's a way we describe the words. So the function value f of a, that is the actual maximum or minimum value, whereas the point is the actual maximum or minimum. Does that make sense? So if I'm asking for the value, I'm just asking for the y value. If I'm asking for the maximum or the minimum, I'm looking for the point. So, for example, on this one, how many relative maximums are there? Just one. There's only one hill, and there's one valley. So there's one relative maximum, one relative minimum. I'll color code them with green. I'll do relative maximums in green, and I'll do the other ones in red. So the relative maximums, that's right here at negative 2 comma 1. So the relative maximum value is 2. The relative maximum is at x equals negative 2, and the actual maximum itself is the point negative 2 comma positive 2. Similarly, the relative minimum value is the y value. It's negative 4, and it occurs at x equals 1. So the relative minimum is the point 1 comma negative 4. Any questions on that? I try to make sure on exams, if I'm asking you for relative maximums or minimums or whatever, I will be very, very clear on it, or I'll give you a space and say like at x equals, so you know just to put the x value. Or I'll say write your answer as a coordinate point so that you know that I'm looking for the actual point itself. So just make sure you're paying attention to the rules of the exam. Any questions on that? All right. So this one, I would like you guys to write down the relative maximums and minimums, if there are any, and if not, just write not available. Yes.
So we go off of what the points are.
Yes.
Okay.
So in this case, I should write that actually when I make a change. Write answers as coordinate points. Thank you, Andre. All right. I have the answers up here if you'd like to check your work. Still working through, that's okay. But these problems were deliberately designed to talk about the situations. So it could be that you have a relative max and a relative min. It could be that you have one of each. It could be that you have two of each. It could be that you have 5 of the relative max and 3 of the relative min. Or it could be you have no relative maxes and a relative min, or you could have none at all. It all depends on the function. So there's no one set guideline. Additionally, relative maximums do not need to have positive y coordinates. They can be below the x-axis. It's okay for that to happen. So don't fret about that fact. So the first one, there's two relative maximums and two relative minimums. At -4, -1, and 0, 3, and then at -2, -3, and 3, 0, respectively. The next one is a parabola, and it's an upward shaped parabola, and it has no relative maximum. Whereas it does have a relative minimum at the very, very bottom of it. And the last one is a nice curvy graph, and it does not have any relative extremum because there's no place where you have a valley or a hill. Any questions on that?
According to the book's definition, or wouldn't the flat part in the last one count?
So this is where things get deceiving. So even though it looks like it's flat, if I were to zoom in on this like to microscopic levels, you'd see that it is actually increasing on the right and decreasing on the left. So this thing is not actually constant between -0.5 and 0.5. It's increasing everywhere. Good question though. Yeah. If it had been like this, if it said like this, oh, wait. A very, very good question. So if it had been like this and then definitively went like that and said that that was constant, then any number between -1 and 1 by the book's definition would be a relative maximum and a relative minimum at the same time, which is absurd. There are times to be absurd in mathematics, but this is not one of them. All right. Next one. Doing the whole kit and caboodle. Just every type of question you could ask. This, if you can do this question by yourself, you're in pretty good standing when it comes to an exam question on the graphing. Because I've told you guys in 126, I always put a graphing problem on every single exam that has like where you have to interpret the data. You have to interpret the graph. So if you can understand this problem, you're doing pretty well. So go ahead and start working on it. I'll slowly fill in details. Keep in mind that's an arrow in the bottom right. It's going down and down forever. People watching the recording, I'm just so you don't have to sit and wait. Just so the people watching the recording can. Sorry about the sound of the recording in progress thing. I'm gonna write some important information here in case you're struggling with this problem. That one. And then next one's we're gonna do next. Have the answers to everything up here if you'd like to check your work. We're going to talk through all of them in just a moment. Does anybody want more time? It's okay if you do. Okay, so domain and range, hopefully we're all okay on that. Domain is all the xi's that get attained by points on the graph. So that's why it starts at -7, but does not include it because there's an open circle up there. Sorry, this graph is really, really bad. This is one of my first graphs that I made in Desmos from like 5 years ago, where I didn't know you could change the size of things. New graphs, they'll have very, very clear, abundant open circles if there's going to be an open circle. And the range is all y values. So since it goes down and down forever, it starts down at negative infinity and then goes all the way up until it reaches a maximum y value of 5, but does not include it because it's an open circle. Then it comes to increasing and decreasing. I'm looking for the places where I'm walking uphill for increasing, downhill for decreasing, and flatland for constant. There's no flatlands. There's no places where it's constant. That can happen. It can be always decreasing. It can be always increasing. It could be any number of the things. So it's always important to check out each thing separately. So it's decreasing on the red pieces. So that's from -7 to -4 in terms of its x values. So parentheses -7 to -4 and parentheses. Then also it's decreasing from -1 to 1 in terms of its x values. So the the interval -1 to 1. And then last but not least, that last chunk, and since it's going down and down and down forever, it means it's going further and further on and on forever for all of its x values. So it's decreasing from 4 to positive infinity. Similarly for the increasing, which is -4 to -1 and 1 to 4. Now the tricky one is the third one, part C. Determine the intervals on which f of x is less than 0. So, important thing to remember, and I'm going to say this over and over in this class, it's going to become annoying to you, I guarantee it, is that a function is less than 0. If f of x means that it's less than 0, that means its function values, its y values are less than 0. So negative y values, that would mean that you're below the x-axis. And so I've made a little grid here. This might seem apparent, but it's good to see it actually in reference. If you are above the x-axis, your function values, your y values are positive. If you're on the x-axis, your function values are 0 because your y value is 0. And y value and function value are synonymous. And then if you're below the x-axis, that's where your y values are negative, i.e. your function values are negative there. So what I'm looking for is where the function is below the x-axis, which is precisely between -6 and 3, and then 6 onwards. And so notice that it's the intervals for like the intervals of x. I should have specified, actually, technically speaking, I should have said, determine the intervals of x on which f of x is less than 0. Or I should say, maybe a better way to write it would be determine the values of x for which f of x is less than 0. Write your answer in interval notation. And so that would be -6 to -3 to +3 in parentheses, and then 6 to positive infinity. Now notice that I didn't include them. I did parentheses. Now that's not because of the rules that we're talking about with increasing and decreasing. Increasing and decreasing, always parentheses. But this has parentheses because it's a strict inequality. It is saying for which values that f of x is strictly less than 0. So I can't include -6 because at -6, f of x is 0. So it's not included. If it had been like this, so I'm going to draw this for just a second. If it had said this, then we would do this. But we can't include infinity, so in infinity we would be a parenthesis. But anyways, and just in case I got any smart Alex out there, if there's interval questions, none of this. None of that. None of that. We're not doing the true false. We're not doing that in this class. Don't let me catch you doing that. And please make sure it's a very clear parenthesis or very clear bracket. Okay? All right. Any questions on that? Yes. What was the name again?
Symbol.
Oh, a union symbol there? That would be allowed. You could use a union symbol, an and symbol, a comma, anything like that. If it specifies to write a union, then use a union, but otherwise you can write in any format. And sorry, what was the name? Connor. All right. One of the most useful things, they're far more common than you'd think, which are piecewise functions. Some books will call it case-defined functions, but that's rare. But piecewise functions. And the definition is spotty at best, but it's best seen through an example. But a piecewise function is, of course, a function. It has to be because it's called one, that is made up of different function pieces on restricted domains. And it's best seen through a specific example. This is a piecewise function. F of x is equal to curly brace, and you have two pieces. You have x plus 3 if x is less than -3, and negative 2x minus 1 if x is greater than or equal to -3. So I call it so usually what I write is that this is piece 1 and this is piece 2. This is kind of my notation, by the way. So you can use I use Roman numerals just to make sure I don't write make it look like it's -31 and greater than or equal to -32. So I'll use Roman numerals, but you can use whatever you want. You can color code it instead. You can say piece red, piece blue, or piece triangle, piece circle, whatever you want to do. But I really recommend identifying them because that'll help you when it comes to graphing them and figuring things out. Now, some jargon. I call x equals -3 a dividing value. The values that split up all the domains of the pieces, those are what we call the dividing values. So just as a step for a second, this function here, this function in example 1.7.6 has two dividing values. It has 0 and 3. The next one has one dividing value, x equals -3. This one dividing value, x equals 2. This one, two dividing values, -3 and 0. And we'll get to the last one in a second. So the function tells you that when you input in x values that are strictly less than 3, we have that f of x is equal to x plus 3. And when we input x values that are greater than or equal to -3, our function magically becomes the bottom one. It becomes piece 2. F of x equals -2x minus 1. So it depends, like the function changes into each piece depending on what the x value is. So when you're trying to compute values, you need to identify which piece you're in. Okay, so example 1.7.5. Oh, it's one of those weird ones. All right. For the piecewise function f described above, find f of -4, f of -3, and f of -3.3 over 2, or -1.5. So at x equals -4, f is piece what? Be careful. I'm glad you mentioned this happened because every problem, be very careful about reading the intervals. Some like the convention is less than, then like go from less than to greater than. But some textbooks and some problems will change it up. They'll do greater than and then less than. So -4 is less than it is less than -3. It is more negative. It is further to the left. So we're in piece 1. So that means that f of -4 is going to be plugging in to the top function, into piece 1. So that'll be -4 plus 3, which is -1. I did not draw a pentagram or a pentagon, so that's interesting. But whatever. At x equals -3, f is piece what? Piece 2, because piece 2 includes -3. Piece 2 is greater than or equal to. So that means that f of -3 is equal to -2 times -3 minus 1, which is going to be +5. And last but not least, at x equals -3/2, which is equal to -1.5. Feel free to use your calculator. I mean, this one not too terrible to figure out, but in if it was like -31/2, -31/2 or -31/5, maybe we want to do a little bit of using our calculator to figure that out. So it's -1.5. That is larger, that is more right on the number line than -3. So it's in piece 2. So f of -3/2 is equal to -2 times -3/2 minus 1. That's going to be +3 minus 1. That's 2. Okay. Example, unless there's any questions on that. You at 150. Yes. So we've got 30 minutes. Can we go 1, 2, 3, 4, 5? We got 5 questions in 30 minutes, 6 minutes per question. I think that's possible. Okay. I want you guys to compute g of -1, g of 0, g of 3, and g of 10. So one thing I will recommend is I will color code this. I'll do this as piece 1, piece 2, and I don't usually write piece 3. I don't usually write the piece portion. I just use the Roman numerals. But you can also, once again, you can color code it with, you can do piece blue, piece red, and piece green. You can do piece triangle, piece square, and piece circle. It doesn't matter. There's some way to identify it in your head. I recommend color because it helps, but it's not required. I'm gonna pull a fast one on you guys. Did it work? I have the answers up here if you'd like to check your work, but if you're still working through it, continue to do so. So g of -1. Oh, wait. 2 answers. I like piecewise functions. I use them all the time. Like all the graphs that you've seen so far, I've been like, those are made by piecewise, like by me making piecewise functions in Desmos. We all should do that. It's fun, right? Do we do that on the weekends? Just go into Desmos and make random graphs. What's your name? Fabian. He's nodding his head. He knows what's up. All right. So g of -1, we're identifying which piece it's in. -1 is less than 0, so we're in piece 1, and there's nothing to plug in. Before 0, for x less than 0, your function is just the constant function 2. It's a flat line. So there's no place to plug in the x's, so it's just 2. G of 0 is not part of piece 1 because that's a strict inequality, but in piece 2, it's a non-strict. It's 0 is less than or equal to x. So we have 0 is in piece 2, and we'll plug it in. If you want to just write the answer, by the way, and do the calculations in your head, that's fine. It's just I'm showing the work so you see what happened. But on the exam, you could just write 1 to be good. G of 3 was the little trick, little mean thing. Be very, very careful about the intervals. Notice that 3 is not included in either piece 2 or piece 3. So g of 3 does not exist. This function is just an open circle there on both sides. And then g of 10, well, that's a number greater than 3, so we're in piece 3. So it's 1 over 10 squared, which is 1 over 100. Any questions on that? And that's, oh, yes, Preston.
So I like voice working with them.
Mhm.
If I took 1 divided by 10 squared and I wrote that as 0.001, would that be?
0.01. That would be fine, but that's only because, so I always like my answers in exact form. And in case you didn't know, this is a really nifty little thing. The only fractions that have a finite terminal, like a terminal decimal point, are ones that are products of 2s and 5s. So if you divide by 20, your function or your fraction will have a finite decimal. Divide by 40, that's all products of 2s and 5s. That'll also be it. But as soon as you do like 27 or 3, 5, it becomes a non-terminating repeating decimal expansion. So fine to work with that, but your calculator should be able to handle converting it into decimal format or from decimal to fraction. But yeah, if it can be written in a decimal format and finite, then sure, that's fine. Any other ones? All right. Oh yes, Andre.
So the X equals 3, so in Alex, that's gonna be the one with like the 0 across or?
If it was asking for G of 3,
Yeah.
you would, yeah, like they usually, if this is type, like this is something that doesn't really happen to Alex. This is something that I'm asking. But if it were, it would probably give you an option that says does not exist, and you can click that. All right. So very cool being able to plug things into them. Yeah, sure, that's fun. But what's more fun is graphing. Much more fun is graphing it. So this is my little method of how to do it. So you're given a function like f of x equals x plus 3, and then negative 2x minus 1 for x less than 3 and x greater than 3, negative greater than or equal to negative 3 respectively. Step 1 is to separate your graph based on the dividing values in pieces. So I'm going to label this as piece 1, and the second one is piece 2. The dividing value is negative 3. And so piece 1 is defined for all values strictly less than 3. So negative 3. So right at negative 3, I'm going to draw this down below. That's piece 1. And then piece 2 includes it. Like that. That's piece 2. And one thing I'll say in here is feel free to draw light lines to separate dividing values. Light lines at dividing values, excuse me. Light lines at dividing values to separate. Because this thing is going to be made of pieces. So it makes sense to break it up based on those dividing values. So I've had plenty of students do this where they just take like a light pencil and they just kind of draw a line through. And you can erase it later on. I'm not going to mark you down if it's as long as it's just faint, like it's not too visible. Or you could use a dashed line to just separate it so you know where one stops and the other one begins. So at the end of the day, I'm going to erase that point. But you don't have to if you're on a time crunch. If you have time, make it pretty, but not needed. Step 2, for each dividing value, plug it into both pieces that it corresponds to. If the piece has a strict inequality there, it's an open circle. If it's a non-strict inequality, solid dot. So remember, strict inequalities are greater than or less thans, and the non-stricts are less than or equal to's or greater than or equal to's. Just in case you didn't know the terminology, a strict inequality is one that does not include the or equal to. The non-strict does include the or equal to. And we'll explain why in just a moment. We'll explain why we're doing step 2. All right. So there's only one dividing value for this function. Only one dividing value. There is x equals negative 3. So at x equals negative 3, piece 1, if I were to plug it into piece 1, it's not part of piece 1. Yes, true, 100%. But if I were able to plug it in, it would be, so y equals x plus 3. So it would be, oh, sorry, no, not negative. So it would be y equals -3 plus 3, which is 0. So it's a strict inequality there. So it's going to be an open circle at -3 comma 0. Open circle at -3 comma 0. I know this is like, if you're wondering why, I'm going to explain it once we get finished with this step. Then in piece 2, if you were to plug that into the function that is defined in piece 2, it would be y equals -2 times -3 minus 1. That's 6 minus 1. That's 5. So there's going to be a solid dot at -3, an x value of -3, and a y value of 5. Right there. All right. So why? Why do this? You can't plug in -3 into the first piece. You can't, remember, it's less than, it's strictly less than, but that means that you can plug in -2.9999999 and sorry, not -2.999, -3.000000000000001. And I guarantee you, if you plug that into your calculator, -3.000000001 into that, you will get basically 0. And so what I'm doing with the strict ones is I'm plugging it in to find where it stops. I'm trying to find a placeholder. When we plug it into the strict inequalities, we're trying to find where it's going to stop. If it were there, it would be a solid dot, but it's not. So we're going to say that's an open circle. That's where it's going to stop, and it's going to get really, really close to that, but not equal it. That's why we do we plug it into both of them, because we need to know where the function piece 1 is going to stop. And it's going to stop at -3. So if I plug in -3 into it, that's going to tell me what the value would be, but it's not there. So it's an open circle. Does that make sense? It's an important little step. Open circles, if it's strict, solid dot, if it's not. And then last but not least is to use your knowledge of functions to graph the rest of it. So for piece 1, or 1, y is equal to x plus 3. That's a line with slope 1 and y-intercept at 1. Y-intercept, sorry, at 3. Now, the reason why I did step 1 above to separate my graph based on it is to remind myself that the piece 1 can only go up until -3 and stops there. It does not continue on. So a mistake that students will make is they'll draw it like this. They'll draw that. That's not correct. That's 2 functions. We want a piecewise function. This fails the vertical line test. It doesn't work. So we have to be particular. So yes, the y-intercept is not part of our function. It's over here, and that's not where we define the red. So instead, we're just going to use the slope to figure out the rest. It's a slope of 1, which means it's a rise of 1 over a run of 1, but you could also think of that as going down 1, left 1 to find another point. And then you can connect the graph with the 2 dots. Like that. So you need to have a slope of 1. So I just went, instead of going up 1, right 1, I'm going to go down 1, left 1 to find the slope. And similarly, for 2, y equals -2x minus 1. So that's a line with slope -2 and y-intercept at -1. So we can plot the y-intercept for the blue because that's part of it. The y-intercept, though, the y-axis is part of the second piece. So I can plot it and then just connect these two dots, and you'll see that, or you don't even need to plot the y-intercept. You could just go down to right one to find another point and connect it. But either way, there you have it. And we've graphed it. Any questions on that? Okay. I'm gonna do we're gonna do at the time. We should have enough time to do all of them, but just in case we don't, we're gonna skip the next the one after this. Which one do you guys want to do? 1.7.6 or 1.7.6? They're both, there's a typo. This should be 1.7.7. Which one do you guys want to do? 6 or 7? 7. The 3-piece one. Excellent. Yeah. All right. Let's identify them into pieces. Piece 1, piece 2, and piece 3. All right. So now that we've done that, I'm gonna do step 1, which is going to be dividing it into the pieces on the graph. So piece 1 is for all values less than -3. That's going to be to the left of -3. What are you doing? Like that. That's piece 1. Piece 2 is between -3 and 0, including -3, but excluding 0. And then piece 3 is from including 0 and beyond. This is just to help me, and you can use vertical lines, kind of separate it up if you want. Make it easier to draw your little grid line at the bottom. But either way, 2 dividing values, -3 and 0. So at x equals -3. For piece 1, y will just equal 1 because it's a constant function. So is it going to be an open circle or closed dot at that point? Open circle, because it's a strict inequality. It doesn't actually exist there. It's a placeholder. So what's the point? Open circle at -3, 1. So we can graph it if we want, or we can wait until the end. I'm going to graph it right away. And then we also have to plug in that dividing value into piece 2. We won't plug it into piece 3 because -3 is not a dividing value for the piece 3. It's only a dividing value for piece 1 and piece 2. So for piece 2, y will equal -3. So that's going to be equal to 3. So it's going to be a solid dot at -3, +3. Because -3 is included in piece 2. Any questions on that? If there are. All right. At x equals 0. This is the dividing value between piece 2 and piece 3. So for piece 2, y will equal -0, which is 0. And it's not included. So it's going to be an open circle at 0, 0. Piece 3, y will equal 0 squared, which is also 0. So there is both an open circle and a solid dot. So the solid dot fills it in. So that point is filled in. So that actually is a point on the graph because it got filled in by the green. Hopefully you can see the difference in color. There's a blue and a green inside. All right. Any questions so far? I've done that to find all the dividing values. Now that I've done that, now I get to work with the rest of it. Now I need to finish the rest of the graph. So piece one is a horizontal line at y equals 2. All right, y equals 1, excuse me. It's a horizontal line because it's just a constant function. So this is where our library of functions and potentially potentially our knowledge of linear transformations may come into play. But it's a horizontal line, so we'll just draw a flat line on the red portion. Like that. 2 is a line with slope -1 and y-intercept at 0. So this one just has a slope of -1, so it goes down 1, right 1, like that. And we've drawn that piece. And piece 3 is a parabola. And you could plug in several points if you want to. It doesn't need to be perfect, but it's got the point 0, 0, and then you can plot 1.1, 1, 1, or 2, 4. Any of those points would be fine. And you'll see that you get this shape. Any questions on that one? That one was tricky. Good. Okay. And so maybe when we get back on Monday, we'll do this example, but we'll finish off with this one. So you can also work backwards. You can be given the graph and create the function. And so it's a similar process. It's just kind of undoing what you just did, undoing it. So what I like to do is first off, so we're given the equation, we're given the graph and we need to create the equation for f. And what I would recommend is breaking it down into its pieces to identify the restricted domains. So that way you know, like, because every piecewise function looks kind of like this. And so it's composed of a function piece and then an interval piece, a restricted domain. So we need to find both parts of it. So might as well find the restricted domains first because those are not too terrible to find. So I'm going to color code it. I'm going to say that this is piece 1 and piece 1 is including -2. That's piece 1. Piece 2 is excluding -2 and then going to 2, but including it. That's piece 2. And piece 3 does not include 2 and goes on forever because of the arrows. Now, here's the frustrating thing about this one is when we look at it like this, we're looking at it in terms of an interval. So the piece 1's interval is parenthesis -infinity to -2 included. But usually speaking, piecewise functions, you like to write the inequality, not the interval. Though I would be fine, honestly, if you said for x in that interval, like that would be fine with me. I'll show you what I mean once we get to the next, once we get to the answer. But technically speaking, we need to convert that to an inequality. That is going to be x is greater than or less than -2. Less than or equal to -2, yes. Piece 2's interval, that's going to be parenthesis -2, comma, +2. So as an interval, that's going to be a sandwich interval. That's going to be a compound interval. That's going to be -2 is less than x is less than or equal to 2. And then piece 3 is going to be parenthesis 2 and beyond, 2 to infinity. So that's going to be x is greater than 2. Any questions on that? Good so far? Okay. Then step 2, now that we've identified the restrictions, now we can just identify the function pieces. So use your knowledge of functions, all the functions that we know and love, to create the equations for each piece. So, piece 1, for 1, it's a line with slope 1, right? You can look at any 2 points and you can see that it goes up 1 over 1, up 1 over 1, or up 2 over 2, and so on and so forth. So you know the slope is 1. And we have, remember, all you need for the equation of a line is either 2 points on it or the slope of a point. We have the slope and we have a point. With point -2, 1. But any point could work. You could also do -3, 0. You could do -4, -1. So we can use the point slope formula. Y minus y sub 1 is equal to m times x minus x sub 1. So that's going to be y minus 1 is equal to a slope of 1 times x minus -1, so plus 2. But this is not in functional form because that -1 is there. So we're going to have to simplify it. We're going to have to write it in slope-intercept form. So this will be y equals x plus 2 plus 1, so x plus 3. And underline it and say that's piece 1's equation. Piece 2 is very quick. Y equals 3. But yeah, y equals 3. For 2, horizontal line with y value 3. So that implies y equals 3. That's it. Nothing needed to do because it's a horizontal line. That's all it is. It's a constant function. Last but not least, for 3, it's a line with slope 2. Right? You can try and find any 2 points and try and connect them. It goes up 2 over 1, up 2 over 1, up 2 over 1, or you could do up 4 over 2. Either way, the rise of the run should be 2 when simplified. And then you could use the point 3, 0. And you might be saying, well, can you use the point 2, -2? Yes and no. It's not actually a point on the piecewise function, but if you're looking at just the equation of that line, it is a point on it, so you could use that point. Line with slope 2, but you can also use with point 3, 0. And then I'll put over here. Could also use 2, -2, even though not on the actual function. You could use it because it is a point on that line, but it's not a point on the curve, the function itself. Does that make sense? The difference? A line has that point, but the function does not. So we're going to do y minus y sub 1. So y minus 0 is equal to m, which is 2 times x minus x sub 1, so x minus 3. Or that's y equals 2x minus 6. And we have all the equations. We have all the domains. We have everything we need. So f of x at the end of the day will be curly brace. For piece 1, it was x plus 3 if x was greater than or less than or equal to -2. It was 3 if x was between -2 and +2. And then it was 2x minus 6 if x was greater than 2. And that is our answer. So you can work backwards and forwards. Whole point. So if you're looking at this from if you're trying to do this one this weekend and you can't remember, Remember what you're trying to do. A piecewise function is composed of different equations on restricted domains. You can find, like, it didn't have to be step one and then step two. You could have reversed the process. It doesn't matter. They're kind of separated but connected. So, any questions on that? All right. We will finish off with this one. If you'd like to have the answer to it, does anybody need me to, does anybody even need this spot still? A little bit. Okay, thank you. I'll put the answer up in just a second. Good. Is that okay? Someone have it now? If not. Good. Good. Okay. If you want the answer, and you can just take a picture of this. Oh wait, no, I got get away from it. So 2, 2, open circle there, and like that. And then 2, -4. And then 0, 0. And it looks like that. All right. That's the answer. If you'd like to check your work, feel free to take a picture of it. Otherwise, if you have any questions, please feel free to email me. Otherwise, you guys have a great rest of your day, a great weekend. Remember that social media actually turned politics from a form of government into a form of entertainment and identity politics. It's not a good idea. Not a good idea. Think about it. Not okay. Not okay. Social media, like politics, is not for entertainment. It's supposed to be a form of government. So that's kind of problematic. Maybe we shouldn't have it. Maybe we should regulate it. Maybe. All right. Have a good day, guys.